So the plan is we're going to look at I pulled out some data that was used to generate the plot. I think not many plots get that designation, but I think the meter plot is sort of the plot. Um, we're going to work through some of the calculations by hand, hopefully highlight some finer points along the way, note what data is not available to inspect. Maybe well, we're not going to look at the updates, sorry. And we're not going to mount a defense against criticism. Those were things that I didn't have time to do, but I would like to if I finish these slides. So what is this method? Like there's a lot of talk about it, but like what is it actually that we're gonna like try to understand in the next 20 minutes? You're gonna collect baselines and somewhat informed estimates of time to complete a task for a human, I should have added there. Then you're gonna take the average of just the successful completions. Then you're gonna use the that time um, to predict the model's success on a particular model success on a particular task. And they're going to look at that success over 8 runs. So generically, it's going to be, it's a 1 out of 8 or 0 out of 8 or something like that, which you might think of as an accuracy. And then there's going to be a kind of quasi-intercept and slope, except in a kind of logistic fit context. Then you're going to set the ratio to 4 out of 8 or 50 success or whatever you want your success to be. And then you are going to solve, you can solve for the intercept, which is the time horizon for each model. And then you're going to once you've extracted those, you're going to take all those time horizons for models, and you are going to plot it against the release date of those models. And you're going to get a nice, pretty linear fit, and you're going to profit. Um, okay, so this is roughly where I spent my time actually. Um, I'll say I've already done the preliminary, so we're just going to mostly focus on like how they collected the data and how they did these like estimations. And we can like talk about a little bit of the qualitative analysis and external validity. But like maybe the thing that's most important from an AI risk perspective, like is out of scope right now. That's the extrapolation. Like how soon is there going to be something that could like automate a human worker at the level of like a month long task or something like that. So like the forecasting bit of this paper, which while important is sort of being left off. So this is um, maybe a misnomer to call it the y-axis, although you will hear people talk about it that way. It depends which stage of the modeling you're doing, but let's just talk about what data they're collecting. So there's a new task that's introduced in this paper, which I guess I have to revise and say that this actually counts as an evals paper because they do introduce a new eval. I had not totally appreciated that, and I tend to think that like if it's just like using the metadata sort of from the eval, it's not exactly an evals to some purpose. It's not exactly an eval paper, but they do introduce an eval, so it counts. But there are so the one that's introduced is in the green, but then they pull in data which we've covered in past weeks from REbench and HCAST. Note that there is another plot that you might see, I think, on the website page for that introduces this whole thing, where actually the HCAST seems to go like this distribution over here seems to be a bit different. It's sort of like it seems as if maybe HCAST like sort of extends in some ways beyond REbench. Um, so I'm not sure what to make of that, but I just want to note it. Also, they noted in the paper themselves, but there's this kind of this low point here where there's just not a lot of coverage in this range. Um, um, the task that gets introduced here is software atomic actions. Um, and while there are very relatively many, right, you can see here, um, uh, they are broken down into just five families. So you might think of these as like each like a little like mini eval. There's and another detail here is that compared to what we've seen before, these are like typical benchmark tasks, right? Where, you know, increasingly uncommon, but you used to just like put something in the prompt and collect up, and then like ask for a certain formatted answer at the end, and you'd kind of you do some regex matching for the answer, and you'd get your answer and you'd score it. So these are, it sounds like just from reading the paper, it's just kind of like one completion. And while there is potentially some reasoning, it's not like calling out to tools or anything else like that. So these are the five different families, and they're multiple choice questions as well as these sort of fill in the blank ones. Um, uh, I'll let you all click out to that later. But RE Bench, they have a nice table in the paper for this paper, just reminding you of what all the RE Bench tasks are. I mean, there's just seven, so they can write it up, for each one what they are. Um, and then where did the baselines come from? They reuse these HCAST baselines that are from contractors. There is on the HCAST one, you had to take a sort of like a qualifying, you had to do a qualifying test task. So that's sort of on the basis which they make this claim that they're domain professionals because they've like successfully completed a task within the domain. And then there's this sort of interesting um, point that they make in the paper about RE Bench, which is like, I don't know if they maybe just didn't think to include, they hadn't like yet thought about the time horizon paper when they were doing the RE Bench paper, but they, rather than having sort of success as the sort of the desired thing, they said like do the best you can with a certain fixed amount of time. And so you might ask whether or not the time estimates are exactly directly comparable. Um, and this is how they end up uh, making it work, is by taking a sort of an average over those who seem to have done it within the right parameter, roughly the right parameters of time. Um, Also interesting, I did not realize the RE Bench baseliners actually do have AI tools. So that's interesting. And then Meter Staff does these software atomic actions. Uh, okay. So like, what does this actually look like? If you're following along on the slides, you can click to it. I've linked to the GitHub repo for the hypothesis testing. It's one of the few from HCAST that they sort of fully document, so you can see the real thing. And what they do is they get multiple runs, and these numbers are in minutes. So two of these contractors in HCAST completed this mystery function number one successfully, right? And for one, it took them 7 minutes, and for another, it took 10 minutes. And then they take the geometric mean of that, um, of the correct. I don't know. I think this is meant, I don't know why there's variation between, I think I just, uh, it must have rounded down. I'm sorry. This should be another precision, but in any case, these should be the same in this case because right, there's only correct answers, right? So it should, maybe it's the point four is hidden here, but in any case, these are equivalent. But here you can see, there was someone took 21 minutes and it was not successful, so they don't count it in the geometric mean. Um, this is the geometric mean I have calculated. Interestingly, this is the number, it's the human minutes, as it appears in that data set I linked to, um, for this task, for the human baseline. And it's different, which is interesting. I don't know why. I haven't really gotten a chance to go and look at it. These are like really central parts of the kind of the estimation structure. So, if I'm almost certain that I've just done something wrong. But it's interesting that they're not the same. They're close. It might be due to, I say this in the next slide. Wait, so actually, let me just pause here and say, like, does anybody have a question so far? I'm trying to make this like very understandable. Is everybody following so far? Yeah. Okay. And I'm sorry if this is like almost too basic. But I feel like sometimes the details you discover interesting things when you're going really slow. It's probably due to the time precision. Like they aver in the data set, they have the difference between started at and completed at. And so if you take the difference between that, which I've done here, it's like 7 and 10. But presumably like there's like seconds that is like causing that difference from which they calculated the human minutes. But I did use the log geometric mean. Um, Oh, also note that these aren't the same humans, so it's not like run one was, did the human, this wouldn't be like human one, right? There are different humans that are being allocated to these different tasks. They allocate themselves. An interesting thing you might want to know is like which ones were doing the same tasks, who here is making it, presumably they are um, if it's only the correct ones, it's the more skilled contractors who are going to be successful. So like there might be a really strong factor here of just like, I don't know, 5 or 6 different contractors that are like causing this like, multi-million dollar plot to like change. So it'd be interesting to know that. Uh, um, yeah, and then baselines are calculated for just as little as two successful runs in many cases, right? I mean, I kind of picked this one at random, but it's just hard to get baselines for anything, human baselines. And so in many of these cases, you're just getting 2 data points. You're taking the average between 2 data points, and I don't know, it kind of feels like it's like not enough to me. I encourage you to check out Appendix C2. I forget what's there, but it seemed relevant at the time. So then we calculate these geometric means. Uh, Forward, we will just like take these values rather than the ones I calculated. We'll just assume the ones in the data set, and then we'll continue to understand. Um, so this is what it looks like for a estimation rather than a baseline. And so what happened? No one um, there's a time that it took somebody to score like a little bit, but that wasn't enough to meet their threshold. So their score is just zero, and they don't have any qualifying uh, what they would count as qualifying successes. So I guess they stare at this and they did do like some quality assurance, I guess. And I presume somebody successfully did this and they knew like meter staff like knew roughly how long that was supposed to take in a sort of unbounded way. Um, and so they sort of backed out like a time estimate from that. But this is not really in like the figures, it's not very well documented. And this would like I'm not sort of suggesting that those are uh, unrealistic or unreasonable estimates. I just don't really understand how they were come at. And just these are denominated in minutes. So this is 10 hours, this is 18 hours, and this is 4 hours, right? Um, and this is sorry for the continue pattern task, which you can hear them describe briefly in the paper. Um, okay, so this is more detail from the paper about how they get to that. They use similar tasks with successful baselines, but in this example that I just pulled out, um, there weren't. So it looks like there were some successful cases here, right? I guess it still didn't meet their threshold. Um, Come to think of it, actually, so it's still a problem here. But there were no successful runs, according to them. So, like, how do you sort of judge it then is a little bit hard. Um, but okay. Um, and I just, just how much does this affect the overall data set? I did a quick run calculation, and it's about 15%. of the non-human, right? So we're going to be using these in other cases. So of the non-human runs, 15% of them are based on these estimates. So it has like a meaningful impact on the overall model that they're making. Okay. Oh, and probably presumably you have to add the weighting, which I'll get to. And this is equally distributed over this 15% is equally distributed over all the models, right? So it's 15% of all of the fits that all of the time horizons that are fit. Okay. Um, okay. So here's like a real example on the mystery functions for Opus 3. And you can see like some of the mystery functions are it like seems to succeed at. Mostly, and some not very often. And these are R8 runs. So pretty straightforward. And then these are I'm carrying forward these like human minutes. So these are the figures. And yeah, I mean like you do see that there's like, well, things that it seems to succeed more at take the least time, at least, right? So that's interesting. And the things that it succeeds most rarely at takes the longest time, or one of the longest times, right? So there's a rough correspondence there. This is Sonnet 3.7, total saturation, right? So it just gets it all right, which is interesting. Um, and we'll compare these two. We'll like use this as like a case study. Um, I thought this was interesting, not described in the paper, but like look at the difference in number of tokens, right, between Opus 3 and Sonnet 3.7. There's a lot more tokens. This is roughly 10x or so. So that's the effect of all this like, reasoning training that they're now doing, right? Which was at the time somewhat new. Um, and probably, I mean, I don't know. You could imagine that there are cases where they've made this more efficient, but like a lot of that performance was just keep working, just until you can possibly feel confident, just keep working. So there's a lot of tokens compared to the Opus tokens. Okay. So ignore right now the curves that are fit. This is just I forget which figure this is pulled out of, but so like all we have now are these like roughly these like this histogram underneath. And so like we have these like bins, right? Like we just looked at one task across two different models, but like there's many of them, and so some of them they're going to already be saturated, on even at Claude, Opus, and um, but some that it can't hardly do at all or never succeeds at, right? And then you can like sort of construct these bins. It's kind of hard to do that, but this is the log scale, so these bins have sort of varying width, but and then you can sort of even just do like uh, a confidence interval on those like sort of empirical summaries. And yeah, it's you can see that when we take a peek later that um, the fits for this logistic fit seems to correspond to these bins. Okay. And you don't see it here, but if you look at the figure that these come from, you can see that in some of the other models, there's this like big like kind of it sort of looks like this, but actually earlier, where you find that there's just like this big knee that happens at 1 minute across many models. So something about where um, that software atomic actions task shifts to like the data points for the runs for that sort of shift to the HCAST ones. You see this like big drop off. So like maybe that would make you think like maybe the model just like treats these as like sort of fundamentally different tasks. Indeed, one actually does like maybe tool calling and that sort of stuff. So there's lots of reasons to believe that's an important difference. What that means for the overall like long-term forecast, I don't know because of course that's at the beginning of the total time horizon that's sort of being estimated. Okay, now we're going to do the estimation um, twice. So the first thing is that we need to take those human times and the success rates that we see for a particular agent and task, and we want to fit a bunch of we want to make a bunch of fits and get a bunch of these parameters. Um, uh, and um, I think maybe the way to think about this is that um, when this is zero, right? So when the or actually I should probably start with this. So the t task is the geometric mean of the successful human baselines, right? So this is our um what the that's the nine or the thing, the human minutes, right? And then we're going to fit this term, and we're going to find parameters for those. And where this is when these two are equal, then that is zero. The sigma then the zero times anything is zero, and then the sigmoid of the zero is zero point 0.5. So that is when there's a 50% time horizon, right? Um, and roughly speaking, this is a um, sort of intercept term, and this is a sort of slope term. Okay. So, short on time, it was edifying to work through this myself. I encourage you to look at it if you're confused. But I'm going to skip this. I'm just sort of working through an example of like, okay, so we know we can find from this here that the time horizon is 6, so we can sort of plug that in. Um, and um, we can find kind of what these values are and calculate the difference. So in this case, this is a task which is a little bit harder than its 50% success rate because it takes like uh, 9 minutes or something like that. And I do the same thing guessing with the beta, which is the sort of slope. And just to come back to it, you can see that there's a different slope here. So the steepness of the of Claude Opus, it's more gentle in the sigmoid versus Sonnet, which is sharper. So there's a kind of a term that is trying to position where this S is supposed to be, left to right, and then there's a term that's trying to tell you how steep the curve is. So you're fitting both of those. And then after you've done that, and this is where the code in which it happens, right? I'll note here in passing that they use regularization, which is just a way of dampening some of the coefficients that seem to matter less across all the models. So they're trying to prioritize ones that seem to be the best, which I guess should have good properties. I haven't thought about it very much. And then they use these sample weights, so they have this diversity score. If you go to that table, that tidy table, they have all these weightings, which is like they want to distribute evenly across all of their task families. So, in order to do that, if you have a task family with many different tasks within it, you would then sort of downweight those tasks because cumulatively you want them to only count for so much. So you have to add that in the model fit term code. So that's what they've done. And so that's where we get these nice curves. Um, uh, and yeah, I think we've more or less already discussed this. Now we want to like come back and we want to get from this the model-wise time horizon. So what we do is we set this term this is zero. I'm sorry, this is zero point 0.5, which in a sigmoid would be zero. So um, uh, this interior would be set to zero, um, and you would solve given the fitted parameters. Um, you could do this also for zero point 0.8 or what have you. Okay. All right. So now you have your this is the code lines. Um, it turns out that they do a slightly different parameterization, and so it's kind of it's the this is a simple way of calculating it. So the quantile here is just declared elsewhere as like 0.5, right? And so it's just the difference between, in this case, this would be zero right? Or is it one? I don't know. I can never remember. And then I'm not going to try to do this right now, but it should, I think it seems to reduce to just the simple quotient of the intercept and the coefficient. That's the two parameters that were fitted. Okay. And then the easy part is that you just do this, you take all those model-wise time horizons and you fit the simplest thing possible, right? Just a linear fit. You just have your alphas and your beta, and from that is where they get this like a um, forecast and and kind of or kind of nowcast. Okay, so that's how it's done. So let me just stop there, see if anybody have any questions or want to say anything. Okay. All right. So of course, then you see this, which is very interesting. And now we know, hopefully, how it's created. Um, the release dates are just, they have some definition for what the release date is. Um, and they've done some bootstrapping to try to determine whether or not it's sensitive. Okay. So other things that are interesting in the qualitative analysis, um, you might worry that the models but so they look at one like from between different models, like why do they fail, and like I don't know, just trying to see where that came from. And I thought was interesting here that it's sort of, well, first thing to remember is that the overall they sample only failures, and that the distribution of failures is going to be different between GPT-4 and O1. So, but they sample 31 from each, or 31 and 32 from each, and then they sort of categorize them. And of the ones that they failed at, you can see that they sort of trade off almost. Everything else seems roughly equivalent, but they seem to trade off. GPT-4 just seems to like repeat itself, whereas where O1 seems to like lose interest or something like that. They have some detail about what is this like premature task abandonment, what goes into that. External validity. Um, So mostly I'm just thinking about the messiness factors, which I think is underappreciated in this paper in the discussion around it, which maybe I'd like to come back to if we have to, in our discussion. Um, there are like lots of other reasons that a task might be difficult. It might be difficult because um, there's like more about like you have to like gain too much context for it, and so you can't understand it ex ante completely. And whereas like some tasks, like everything is specified, you could sort of do it in a vacuum or something like that. So they go through trying to find different messiness factors to see if like the difference in time horizon is really just comes down to these other factors. Um, and here's a couple examples of that. Um, this is this resource limited sort of gets at what I was just discussing here, but um, you have to. So anyway, so the meter people went back and went through and classified them, trying to find out kind of all of these things, and they added all these messiness scores together, and then they rated, each task as sort of having a certain messiness, and when they plot it, it turns out to not really matter very much from the release date perspective. So when you I'm actually not sure what weighted success rate is in this case. Maybe it's the weighting that we were just discussing with the task diversity, but in any case, um, yeah, and each of these different shapes is a different model. And I'm sorry, I kind of cut off the legend here. I could go find it if we're interested to discuss this. So what do you notice here? You notice that while the most messy tasks are less successful, the models on average are less successful at those. Nonetheless, you see, roughly this kind of linear fit. You could probably make out a similar linear fit. They don't actually do. probably could have or should have just like compare like what's the kind of the R squared on these two different fits just to sort of demonstrate their point, but you can sort of see it by eye. Okay. And then discussion. Um, Here's some questions. It sounds like we've all read this, so now we can sort of talk about the more kind of theoretical properties of this paper or more speculative. Um, I've linked for you all this excellent interview I recommend, where I've taken some of these questions from. But there's also, I'll just click out to it now, this document that I think one of the lead authors, I think Ben West is the other one. Um, I was getting some feedback, and so tries to address them here. So uh, maybe we can, you know, try to guess what the answer is, given what the question is. Okay, but that's all I have. So thank you. That's it.